Hi, my name is Cassie Wood. I'm a student at the University of Illinois in Springfield, and today I'm going to make a video to show you how to analyze data from mass spec, IR, proton NMR, and carbon-13 NMR, and use that data to determine the structure of a chemical compound. So we are going to be using all of that data to determine the structure for C6H35N. So this is our first graph. It is mass spec graph. What I like to do first is I like to figure out the DOU first, and that's really easy. You just take the number of carbons times 2 plus the number of nitrogens minus the number of hydrogens. And if you had a halide, you would minus the number of those. But since we don't have a halide, we're just going to leave that off. And then you take all of that and you divide it by 2. So in this case, our DOU is 0. So that's really helpful because it helps us to determine that there is really just alkanes in this chemical structure. There's no double or triple bonds and there's no rings. So now that we know the DOU, I like to determine the base peak and the M+. So the M+ is always this one farthest to the right. So our M+ is 241. And our base peak is usually a large peak somewhere kind of in the middle. So our base peak is at 142. So after we figure out those two pieces, I like to determine any fragments that we have. So here we see 212. If you subtract 214 from 212, you get 29. So an M-29 is a good indicator that there is a bond between CH2 and CH3. A good chart to find, to use to determine fragments is, I just use Google. I Googled mass spec analysis chart and found this in the images. So this is very helpful. So you can see here at 29, we've got a CH2 bonded to a CH3. So that's one of the indicators that that's going to appear in our chemical structure. If we look back at our chart, we can see that there are a few other fragments. We usually don't look lower than the base peak because there's not much going on. They're very small little blips on the chart. But 44 is an indicator that there is a carbon-carbon-nitrogen bond. And 57 can indicate that there is a 4-carbon chain. And that is pretty much it for this mass spec graph. There's not a lot of peaks to go off of, but we've got our main ones, and those will be very helpful in determining the structure of this compound. We're going to look at IR. So in this chart, there are 5 specific zones that we will look at to determine what we will find in our structure. So we work from left to right because it's easiest. And in zone 1, we've got this little blip here, which determines that there is a secondary amine in this compound. There's no dips for an alcohol, which we know because we don't have any oxygen in our compound. But it's nice to keep an eye out for. So no OH in this, but there is an amine. In zone 2 is where we're going to find a peak, which indicates that there are alkanes in this compound. So we see these big peaks here. Next we move on to zone 3, and there's nothing going on in zone 3, so we know that there are no triple bonds. Next, in zone 4, there's really nothing going on in zone 4, so we know that there aren't any double bonds. But here in zone 5, you can see up here, this points to an amine. So we know that there is going to be an amine. We know from zone 1 and from zone 5 that there is going to be an amine in this compound. In this region over here, we call it the fingerprint region. We don't really use this to determine anything. We don't really look over here to determine. So I'm going to just cross this off. Here is the graph for proton NMR. And so I've already written down what we find at each spot. So we've got a lot of singlets here, which is very nice, because once you get into doublets and triplets and multiplets, it gets more complicated. So here, I really like this chart because it shows how many hydrogens we can expect to see at each point. So this first one has 6 and 20 and 4 and 1 and 4. So based on this, as well as the mass spec and the IR graphs, I've come up with this structure. And based on this structure, we can determine that the 3 hydrogens on either end correspond to this spike with 6 hydrogens. We can determine that these 5 sets of hydrogens on this side, as well as on this side, will correspond to this second spike with 20 hydrogens. Then because it is more deshielded, we know that the hydrogens in this group and in this group correspond to this spike here with 4 hydrogens. And then because there's only 1 hydrogen here, we know that that has to be from the amine. And then getting more downfield, we have the more deshielded hydrogens in these 2 groups right here next to the amine. So that corresponds to this spike. So here's the last graph for carbon 13 NMR, and I have already numbered the carbons as to which spike I think that they correspond with. So using the same structure that I determined for the last graph, I still think that that is correct. We can see that there are 6 major spikes corresponding to 8 different carbons on each side. So because it's just a chain of carbons, it's a lot easier to determine which carbon corresponds to which spike in the graph, as opposed to a more complicated structure. So the farther we get from the nitrogen, the lower these numbers go. So you can see at 14, we're going to have this farthest carbon, and that just is going to continue. And we see that spike number 5 has 3 values for it, so we can assume that that is indicating these 3 carbons here. And finally, this carbon here, this spike here, represents this carbon that's closest to the nitrogen. To determine this, I used another chart that I found on Google. This is the chart, and really you can find one of these charts for carbon NMR, proton NMR, IR, and mass spec, and they're really helpful. And if you count it out, there are 16 carbons, 35 hydrogens, and 1 nitrogen. And that's how you use mass spec, IR, proton NMR, and carbon 13 NMR to determine the structure of a chemical compound.